because we have run out of material to cover in lecture, we will get started and do the review and get it posted, and then the homework for chapter 26 is due on the 27th, which is Monday. The exam is scheduled for Wednesday, the 29th. So honestly, if we're getting the review done today, I've got the exams ready. You can do it anytime you want next week. So if you want to do it early, I have no problem with that. You get one sheet, double-sided of notes. As a formula sheet. You will need a calculator. And then lab today is for makeups, but the only person who needs to make labs is you doing it. We can get to that. So let's start by reviewing chapter 25. So electromagnetic waves are traveling waves of oscillating electric and magnetic fields. Electric and magnetic fields in an electromagnetic wave are perpendicular to each other and to the direction of propagation and are in phase. You can use the right-hand rule to get the direction of the fields and propagation. An accelerated charge will emit electromagnetic waves. Electromagnetic waves can travel through the vacuum. Their speed in a vacuum is always the same. It is the speed of light, 3 × 10⁸ meters per second. The Doppler effect is the effect of change in frequency of electromagnetic waves by relative motion between the source and the receiver. The change in frequency. So the final frequency is the initial frequency times 1 plus the speed over the relative speed of motion between the two objects over the speed of light. So the change in frequency is the velocity over the speed of light times the frequency. Frequency goes up, becomes higher for things coming towards you. Frequency goes down, becomes lower for things traveling away from you. Electromagnetic waves can have any frequency. So if a star is emitting light from excited hydrogen at a frequency of 4.57 × 10⁻14 hertz, if you're moving away from the star at 3,000 meters per second, what change in frequency will you observe? So the frequency is the base frequency times 1 minus the speed over the speed of light. Because you're going away from it, it's minus. So the change in frequency is just the new f prime minus f, which is just f times minus v over c. So 4.57 × 10⁻14 hertz times minus 3,000 meters per second over 3 × 10⁸ meters per second gives you negative 4.57 × 10⁻⁹ hertz. The entire range of frequencies is called the electromagnetic spectrum. The named portions of the spectrum from the lowest frequencies to the highest are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The relationship between frequency and wavelength, the speed of light equals the frequency times the wavelength. It's actually the case for any wave. Their speed equals their frequency times their wavelength. But for electromagnetic waves, that's going to be the speed of light. The energy density of an electromagnetic wave is 1/2 epsilon naught times the electric field plus 1/2 1/2 mu naught the electric field squared 1/2 mu naught times the magnetic field squared. And it turns out that these components have the same energy, so it ends up being epsilon naught times the electric field squared or 1/mu naught times the magnetic field squared. Light with a wavelength of 400 nanometers has what frequency? So here, speed of light is frequency times wavelength. Frequency is going to be speed of light divided by wavelength. The frequency is 3 times 10 to the 8th meters per second over 400 times 10 to the minus 9 meters, 400 nanometers, which is 7.5 times 10 to the 14 hertz. What is the energy density of an electromagnetic wave with an electric field amplitude of 4,000 volts per meter? And epsilon dot is 8.85 times 10 to the minus 12 coulomb squared over Newton meter squared. So energy density is 1/2 epsilon naught E squared plus 1/2 over 2 mu naught B squared, or epsilon naught E squared plus 1/2 1 over mu naught B squared. We know the electric field amplitude, so we want epsilon naught E squared. So energy density is going to be epsilon naught times the electric field squared. So 8.85 times 10 to the minus 12 coulomb squared over Newton meters squared times 4,000 volts per meter quantity squared. That is 1.416 times 10 to the minus 4 joules per cubic meter. And the relationship between the electric and magnetic fields in light is the electric field ends up equaling the speed of light times the magnetic field. The intensity of an electromagnetic wave is the energy density times the speed of light, because it's the rate at which energy is being deposited. So it's energy density times speed. So 1/2 speed of light times epsilon naught E squared over 1 over 2 mu naught C B squared, or C epsilon naught E squared, or C over mu naught B squared. And the momentum of an electromagnetic wave is the energy over the speed of light. And with that, we can determine the radiation pressure, which is the average intensity over the speed of light. So what is the intensity of an electromagnetic wave with an electric field amplitude of 4,000 volts per meter? So once again, we're going to use the version with just the electric field. Intensity is energy density times the speed of light. So epsilon naught times the speed of light times the electric field squared. Intensity equals epsilon naught C E electric field squared. So 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared times 3 times 10 to the 8th meters per second times 4,000 volts per meter quantity squared gives us 4.284 times 10 to the 4 watts per square meter. And what force does a radiation pressure from light with an average intensity of 1,500 watts per square meter exerted in an area of 50 meters squared? Well, the pressure is the average intensity over the speed of light, which is force over area. So the force is the average intensity over the speed of light times the area. So 1,500 watts per square meter divided by 3 times 10 to the 8th meters squared times 50 square meters gives us a force of 2.5 times 10 to the minus 4 newtons. And the polarization of a beam of light is the direction of its electric field. And a polarizer only transmits light whose electric field has a component along the polarizer's axis. And an initially polarized beam of light encountering a polarizer at angle theta has a transmitted intensity of I naught, the initial intensity, times the cosine of that angle squared. So if that angle is 0, if they're lined up, all the light goes through. If the angle is 90 degrees, all the light gets blocked, and so on. And if it's 45 degrees, it's square root of 2 over 2. You square that, and you get a half. So, vertically polarized light with an intensity of 5,000 watts per square meter passes into a polarizer set at an angle of 78.46 degrees to the vertical. What is the intensity of the outgoing light? So for this, intensity of the outgoing light is incoming intensity times the cosine of the angle squared. So 500 watts per meter squared times cosine of 78.46 degrees squared. The cosine of 78.46 degrees is 0.2. So multiply by 0.2 twice, you get 20 watts per square meter. And the transmitted intensity of an initially unpolarized beam of light going through a polarizer is half the initial intensity. And light scattered from the atmosphere is polarized when viewed at right angle to the sun. And when light reflects from a horizontal surface, it's partially polarized in the horizontal direction. Unpolarized light of intensity 500 watts per square meter passes through two polarizers set at 45 degrees to each other. What will the intensity of the outgoing light be? So for this, there's two stages. Intensity 1, in between the two polarizers, is going to be half the incoming intensity. So half of 500 watts per square meter is 250 watts per square meter. Intensity 2 is intensity 1 times the cosine of the angle between the two polarizers. That's 250 watts per square meter times the cosine of 45 degrees squared. Cosine of 45 degrees is square root of 2 over 2. Square that, you get a half. So 250 watts per square meter times a half gives you 125 watts per square meter. Any questions about chapter 25? Nope. Okay, we'll go on to chapter 26. So, a wavefront is the surface along which the wave phase is constant. You can think about it as sort of this expanding sphere from a light source or something like that. You can draw rays that are perpendicular to the wavefront that indicate the direction of propagation. Using rays, you can do geometric optics. When something reflects, the angle of incidence equals the angle of reflection. Thus, the image formed by a plane mirror is upright, but appears reversed left to right, and appears the same distance behind the mirror as the object is in front of it, and is the same size as the object. It actually only appears reversed left to right because we expect it to be rotated 90 degrees. What actually happens is that it's reversed front to back. And that's what we're seeing that makes it look like it's mirrored, reverse left to right. So light hits a mirror at an angle of 35 degrees to the normal. Well, what angle does it reflect? Well, angle of incidence equals angle of reflection. And that will be 35 degrees. Now, spherical mirrors have a spherical reflecting surface. You can have a concave mirror that's curved inward and a convex mirror that's curved outward. So a concave mirror is one where the mirror is on the inside surface of the sphere. Convex is one where it's on the outside surface. The focal length of a convex mirror is half the radius of the sphere and negative. For a concave mirror, it's half the radius of the sphere and positive. Convex mirrors have a negative focal length because the focus is on the far side of the mirror. Concave mirrors have a positive focal length because the focus is on the near side of the mirror. An image is real if light passes through it, virtual if it does not. The image you see as a reflection in a flat mirror is virtual. The image formed here on the board is real. The mirror equation is for an image, 1 over the distance to the object plus 1 over the distance to the image equals 1 over the focal length. And the magnification is minus distance to the image over distance to the object. And the sign of the magnification tells you whether the object is upright or inverted. If it's negative, it's flipped upside down. It's inverted. So for a convex mirror, for any location, the image will be upright, the image size will be reduced, the image type will be virtual. For a concave mirror, if you're beyond the center of curvature, the image will be inverted, the image size will be reduced, the image type will be real. If you're at the center of curvature, the image will be inverted, the image size will be the same as the object, and the image type will be real. If you're between the focal point and the center of curvature, the image will be inverted, the image size will be enlarged, the image type will be real. If you're just beyond the focal point, the image will be inverted, its size will be approaching infinity, and it will be real. If you're just inside the focal point, image will be upright, its size will be approaching infinity, and it will be virtual. Between the mirror and the focal point, image will be upright, image size will be enlarged, and the image will be virtual. So if a 2-centimeter object is 30 centimeters away from a concave spherical mirror of radius 40 centimeters, where does the image appear and what is its size and orientation? Well, we know the radius of the mirror, so we can find the focal length. The equation we're going to use is 1 over the distance to the object plus 1 over the distance to the image equals 1 over the focal length. We know the distance to the object, it's 30 centimeters. We need to know the focal length. The focal length is half the radius, and it's positive because this is a concave mirror. So the focal length is half of 40 centimeters. It is 20 centimeters. So 1 over 30 centimeters plus 1 over di equals 1 over 20 centimeters. So 1 over di equals 1 over 20 centimeters when it's 1 over 30 centimeters. That is 1 over 60 centimeters. Di equals 60 centimeters. The magnification is minus di over do. So minus 60 centimeters over 30 centimeters, it is minus 2. So the image is real, inverted, because it's negative, and it's twice as big. We multiply by the magnification, it is 4 centimeters tall. Any questions about that? Here we have a 2-centimeter tall object, 10 centimeters from a convex spherical mirror of radius 20 centimeters. Where does the image appear and what is its size and orientation? This is convex. So focal length is minus 1/2 the radius. So focal length is minus 10 centimeters. So 1 over 10 centimeters plus 1 over di equals 1 over minus 10 centimeters. So 1 over di is minus 1 over 10 centimeters minus 1 over 10 centimeters, which is minus 1 over 5 centimeters. So di will be negative 5 centimeters. Magnification will be minus di over do. So minus 5 over 10, that's plus 1/2. The image will be virtual, upright, and smaller at 1 centimeter tall, half the height. Refraction is the change of direction of light due to a change in speed. The index of refraction gives the speed of light in a medium, where the speed is c over the index of refraction. So the index of refraction is c over the speed. So the bigger the index of refraction, the slower the light is in that medium. And the amount that light bends when it goes from one medium into another is determined by Snell's law, where index of refraction 1 times the sine of the angle from the normal on that side equals index of refraction 2 times sine theta 2. So what is the speed of light in a material with an index of refraction of 1.5? Index of refraction is speed of light over speed in the medium. So speed in the medium is speed of light over index of refraction. So 3 times 10 to the 8th meters per second divided by 1.5 is 2 times 10 to the 8th meters per second. And glass has an index of refraction around 1.5. So Snell's law, index of refraction n1 times sine theta 1 equals n2 times sine theta 2. Light entering a medium of higher index of refraction gets bent towards the normal. Light entering a medium of lower index of refraction is bent away from the normal. When light enters a medium of lower index of refraction, there's a critical angle beyond which the light will be totally reflected. It will not be transmitted. The sine of that critical angle equals n2 over n1. Where n2 is the lower index of refraction and n1 is the higher index of refraction. So a laser beam passes from air, n equals 1. It enters the sapphire, n equals 1.75 at 30 degrees to the normal. At what angle will it be in the sapphire? Well, n1 sine theta 1 equals n2 sine theta 2. So sine theta 2 will be n1 over n2 times sine theta 1. So 1 over 1.75 times sine of 30 degrees is sine of theta 2. So sine of theta 2 equals 0.2857, blah, 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 blah. Theta 2 ends up equaling 16.6 degrees. Because it bends towards the normal. It's closer to perpendicular. And at Brewster's angle, the reflected light will be totally polarized. The tangent of Brewster's angle is the ratio of the index of refraction theta to n2 over n1. And a lens uses refraction to bend light and form images. Excuse me. And the thin lens equation is 1 over DO plus 1 over DI equals 1 over the focal length. And the magnification is minus di over DO. You'll notice these are basically the same as the mirror equations. The only difference is that positive images are on the near side of a mirror. Positive images are on the far side of a lens. And the focal length, concave lenses are negative, concave mirrors are positive, and convex mirrors are negative focal length, convex lenses are positive focal length. The index of refraction will vary with frequency. Different frequencies of light get bent different amounts. This is called dispersion, and rainbows are caused by dispersion within raindrops, and a bunch of other effects. It's actually a lot more complicated than simple dispersion, but part of the process is dispersion in raindrops. An object 25 centimeters from a lens with focal length plus 15 centimeters, where does the image form? 1 over DO plus 1 over DI equals 1 over focal length. 1 over 25 centimeters plus 1 over DI equals 1 over 15 centimeters. So DI is going to be 15 centimeters, 1 over 15 centimeters minus 1 over 25 centimeters. So 1 over 0.02667 centimeters, which comes out to 37.5 centimeters. And be careful with these. You can make mistakes by not inverting enough times. Much like when you're doing resistance in parallel, things like that. That was chapter 26. Any questions about that? And now lastly, we have chapter 27. The human eye is focused by the ciliary muscles, which change the shape of optical instruments, the shape of the lens. A camera is focused by changing the distance from the lens to the film. Human eye changes focal length. Camera changes DI. The near point is the closest point at which the eye can focus. It's typically 25 centimeters. The far point is the furthest point at which the eye can focus. It's typically at infinity. The F number of a lens is its focal length divided by the diameter of its aperture. So what is the F number of a camera with a focal length of 5 centimeters and a diameter of aperture of 2.5 centimeters? F-stop or F number is the focal length over diameter of aperture. So that will be F over D, 5 centimeters over 25 centimeters. That has an F-stop of 2. In lens combinations, an image formed by one lens serves as the object for the next. Nearsightedness occurs when the image is focused in front of the retina, causing the far point to be closer than infinity. This can be corrected with a diverging lens. A diverging lens is a concave lens that is thinner in the middle and thicker on the edges. Farsightedness occurs when an image is focused behind the retina, causing the near point to be more than 25 centimeters from the eye. It can be corrected by a converging lens. This is a lens that is thicker in the center and thinner on the edges. The refractive power of a lens in diopters, when the focal length is in meters, is 1 over the focal length. A magnifying glass is a converging lens. Its magnification is given by the near point distance, n, over the focal length, if the image is at infinity, or if you make the image at the near point, 1 plus the near point distance over the focal length. So what is the magnification of a magnifying glass with a focal length of 10 centimeters with the image at the near point of a viewer at 25 centimeters? M equals 1 plus near point over focal length. So 1 plus 25 centimeters over 10 centimeters, 1 plus 2.5. That magnifying glass will have a magnification of 3.5. A compound microscope uses 2 lenses, the objective and the eyepiece, to form an image of a small object placed close to the focal point of the objective. Its magnification is given by the magnification of the objective times the magnification of the eyepiece. And the total magnification ends up being the distance to the image for the eyepiece times the near point over the focal length of the objective times the focal length of the eyepiece, with a minus sign. So what's the magnification of a compound microscope with a 20x eyepiece and a 300x objective? This is fairly straightforward. You just multiply those magnifications together. 300x times 20x is 6,000x. A refracting telescope also uses 2 lenses to form an image of a very distant object. Its magnification is given by the focal length of the objective over the focal length of the eyepiece. And the length of the telescope will be the focal length of the objective plus the focal length of the eyepiece. A telescope having a mirror instead of a lens as the objective is called a reflecting telescope. And all big, serious telescopes in use for research today are reflecting telescopes. So a telescope is made of 2 lenses. The eyepiece has a focal length of 5 centimeters. The objective has a focal length of 95 centimeters. How long is this telescope and what is its magnification? Well, the length is straightforward. It's just add up the focal lengths of the objective and the eyepiece. That's 95 centimeters plus 5 centimeters. That's 100 centimeters. And the magnification is the focal length of the objective over the focal length of the eyepiece. That's 95 centimeters divided by 5 centimeters. That will be a magnification of 19. Lens aberrations can distort images. Spherical aberration occurs because off-axis rays do not quite focus, don't focus at this focal point. This can be corrected by precision shaping of the lens, or the addition of extra lenses to reduce the effect. Chromatic aberration occurs because different frequencies of light have different indexes of refraction. It can be corrected by using multiple lenses in an achromatic lens system. Yeah, spherical aberration precisely shape the lens to not actually be spherical. Chromatic aberration, you use multiple lenses in an achromatic lens system. That's part of why camera lenses are so complicated. Any questions about anything? That is the review. I will get that and the slides for this up on Blackboard tonight. Stop sharing and